Hello everyone. In this session, we'll see the internal structure of a typical microprogram sequencer. This topic we have already studied. In the previous session, we had seen the design of a control unit of a computer which follows microprogram organization. Microprogram control organization. Okay, so we have already seen the design of control unit. Now, we have also seen the flowchart for microprogram sequencer. In this block diagram, which is shown over here, this is the last topic of your chapter number 7. So in this block diagram, it is generally, this figure is used for illustrating the internal structure of a typical microprogram sequencer. We know that microprogram sequencer is a next address generator. Okay, so here we are going to see internal. Here we had seen in the previous figure, we have already seen this. I'll quickly relate it so that you can get to know what is this topic about. This figure we have already studied. Okay, where we have a control memory, the address for a particular instruction to be fetched from the control memory, we have the address in the control address register. And who provides this address? The address is provided by the next address generator. So this next address generator, out of the 4 possibilities, provide input to the CAR. Here we had just written that there would be some branch logic which would be providing selection values to the multiplexer, that out of these 4 which one has to be selected. Okay, so now we are going to discuss this part in detail. Is that clear? We are going to see how is this actually happening. How does one address out of the 4 possibilities goes inside the control memory? Okay, CAR, and then CAR is used by the control memory. So let us see this figure. I'll explain you this last topic which is left out. Okay. Now see, in this figure there are 2 multiplexers. One multiplexer is already known to you. This is the first multiplexer which selects an address from one of the 4 sources, and out of these 4 any one would be redirected towards the CAR, that is control address register. Now second multiplexer over here, it tests the value of the selected status bit. See, we said that now we know what are the values of CD, what does BR mean, what does CD mean. Now CD has several status bits. Depending upon the status bit, when you write 00, unconditional jump. Okay, then we are checking the sign bit S, I, and Z. Okay, so when CD, the value of CD is 00, it is unconditional jump U. When CD is 01, I, we check the indirect bit. When CD is 10, we check the status bit, we check the sign bit. And when the value of CD is 11, we check 0 bit. So here, what is this multiplexer for? This multiplexer will tell the result of the condition that is tested. Okay, here we are providing the value of CD. See, this is my control memory. We know that our control memory consists of micro instructions. These micro instructions are of 20 bits, out of which 0 to 6 would be address bit. Then we have 2 bits for BR, 2 bits for CD, and 9 bits for micro operations, F1, F2, F3. Okay, so here in this figure, what they have shown us, out from the micro instruction, from the micro instruction that is selected. Now the CDR also provides the next address information to your next address generator. So this is the information that is provided. You are providing the value of CD from the selected micro instruction. Whatever is the value of CD goes inside this multiplexer. If 00 is selected, this is 1. By default, 1 would be entered over here and the test value would be 1. Understood? If 01 is selected, this is I. What does I mean? Direct indirect bit. Whatever is the value of direct indirect bit, if it is 0, test value would be 0. If it is 1, test value would be 1. Okay? Then comes 1 0. In 1 0, the sign bit value is provided to the multiplexer. If it is 0, test would be 0. If sign bit is 1, test would be 1. Okay, so if it is a negative number, test would be 1. If it is positive number, test would be 0. And finally, Z. Z is what? When CD is 1 1, we check whether the accumulator is 0 or not. So depending upon these four status bits, here we have not written U. We have simply written 1. Why? Because in U means what? Unconditional jump. It's always true. Okay, so 1, I, S and Z. This is my second multiplexer. This multiplexer will provide the test value to the input logic. Depending upon this test logic, add the two values which come from the branch. Look over here. These two lines are given to the input logic over here. Okay, which are the four possibilities in branch? 0 0 means jump. 0 0 means jump. This one. 0 1 means call. 1 0 return. It is coming from SBR. And 1 1 map. So these two inputs, depending upon these two inputs and the value of t, the data will be provided to S0, S1 selection line. And depending upon selection lines, okay, so depending upon the value of t and value of S1 is 0, a particular input would be selected for providing to CAR. Apart from this, these branch instructions, BR values and T will also decide whether to load the value of SBR or not. When should this SBR be loaded? SBR should be loaded only when the value of BR is return. Okay, return means what? The value of BR should be 1 0. Okay, so here these values are again provided to the input logic BR, and this BR, depending upon the value of what branching is provided and the test value. If test value does not fulfill but 1 0, I0 and I1 are 1 0, in that case also this return will not be, this SBR will not be loaded. Okay, so the selection lines as well as the load input of your SBR is dependent only upon I0, I1 and T. I0, I1 are the fields from BR and T is the output, test output of the CD values. Okay, let us see the truth table for it. This is the logic truth table for the microprogram sequencer. Let us talk about BR. We know that BR00 is what? Jump. 0 1 is call, 1 0 is return and 1 1 is map. Now here what we are doing is we are checking the test condition. We know that this jump and call are only affected by condition. Return and map have no significance of the condition value. So in those cases, the value of t is placed across because in dependent upon CD values, return and map are always going to take place if it's written. Okay, but jump and call will only take place if the condition is true. So here this input logic has three values I1, I0 and T. If I1, I0, look, recall the figure. I1, I0 and T. I told you that depending upon this input logic I1, I0 and T, a particular input would be selected. Selection lines, a particular input would be selected and the load of SBR would be decided. Okay, so this I0, I1, if BR value is 0, 0, I0, I1 में 0, 0 जाएगा. If the condition is not met, T is 0, whatever CD value you had provided, whether it is S, I, Z, if any of those values is not met, what would happen? Your selection line would be 0, 0. Why it is 0, 0? because 0, 0 is what? The next address. Look over here. When selection line is 0, 0, this would be selected. CAR would be incremented. So if none of the condition is met, your branching will not take place and you will be moving to the next micro instruction. Okay, in sequence. So whenever condition is not true, what happens is you will not branch to a particular location, you will simply move on to the next address. So next address means what? Your selection lines should be 0, 0. Only if selection line is 0, 0, CAR will be incremented and that will be provided over here. Okay, now let us see what if 0, 0 is jump. Okay, condition is also true. If condition is true, now what I want is, I want this thing to be entered. What is 0, 1? Let us see in our multiplexer figure. 0, 1, this one. If condition is true, what would happen? Whatever is the address, this address would be passed to the CAR. My first input is this one. Okay, so this line, if my condition is met, अगर मैंने लिखा है jump to this particular location, jump fetch, so that fetch वाला address is fetched from the micro instruction and your control will be transferred to that address. Okay, so what was that? Branch should be 0, 0 and T should be 1. If branch 0, 0, T1, I want this thing to be transferred to CAR. So my selection lines should be what? 0, 1. Look over here. Understood? Now, let us see the next one. If branch is 0, 1 and condition is not met, branch 0, 1, true test condition is false. So in that case, again, 0, 0 should be selected. What does 0, 0 mean? Next address. Okay. In all these cases, load of SBR should be 0. SBR should only be loaded when you want to store the return address. Okay, let us see over here. Next, 0, 1 is what? Call. In this case, 0, 1 is call and test condition is also true. So in this case, what we need to do is load the SBR with the next address. Before you jump to a particular location, call means what? You want to go to that function and come back. If you want to come back, you need to load the SBR value. Okay, so where will you jump to? You will jump to the address provided. So if address provided in the micro instruction. Okay, that function would be called. So 0, 1 again is what? Address. So look over here. When I0, I1 is call, that is 0, 1. Test is also true. When test is true, what should be transferred to CAR? This address. This address should be transferred as well as SBR should be loaded. Okay, what will SBR be loaded with? SBR will be loaded with the next address. And this AD will be transferred to CAR. Fine. Now, moving to the next one. 1, 0. 1, 0 is what? Return. When 1, 0 is returned, irrespective of the value of T, the return wala part in your multiplexer should be selected. So what did we provide as a selection line to mux 1? 1, 0. Let us see what is there in 1, 0. 1, 0 is this one. Where is this line coming from? It is coming from SBR. So whenever return is there, whatever is the value of SBR would be transferred to your multiplexer. Through your multiplexer will be transferred to your CAR. Clear? And last one is what? 1, 1. What was 1, 1? Mapping. Irrespective of the test condition, when 1, 1, select 1, 1 from the mux. In all these cases, your SBR should not be loaded. SBR is loaded only when call is taking place. So 1, 1 is 3. Whenever the value of I0, I1 is 1, 1, this particular external mapping should go inside the multiplexer and be transferred to CAR. So this is all about the internal architecture of internal structure of a typical microprogram sequencer. Okay, and after this table is ready, what we have done? Equations for S1. Now you can frame the equation of S1 based on I0, I1 and T. So when you see when you see the value of S1, what is S1 equal to? It is equal to I1. What is S0 equal to? S0, these three phases. Okay, when you simplify it, you will be getting I0, I1 plus I1 dash T. And what is load equal to? When should load be 1? I1, I1 dash, I0 and T. So these are the three equations. So this is your internal construction of your microprogram sequencer. And this ends chapter number 7, the last topic. I hope you have understood it.